This call is now being recorded.
Okay. So today we are going to discuss the numericals at the end of the chapter, that is the basics of the heat transfer. So I will show you the question here in the PPT. So are you able to see the PPT now?
Yes, sir.
Okay. So let's move to the numerical now. So So the problem number one, it is given that there is a hot combustion gases of a furnace which are separated from the ambient air and its surrounding, which are at 25 degrees centigrade. So here the ambient temperature, that is T infinity, and T surrounding both are equal at 25 degrees centigrade, and it is being separated by a brick wall which is 0.15 meter thick. It is given that the brick is having a thermal conductivity of 1.2 watt per meter Kelvin and has a surface emissivity of 0.8. Under steady state conditions, an outer surface temperature of 100 degrees centigrade is measured. So, free convection heat transfer to the adjoining the surface is characterized by a convection coefficient of H equal to 20 watt per meter square Kelvin. So, we need to find what is the brick inner surface temperature. So, if you see here, if we draw it here, there is a brick wall. There is a brick wall, and it is 0.15 meter thick. Okay. And in the question, it is given that its thermal conductivity is 1.2 watt per meter Kelvin. And it is given that the outer surface temperature is 100 degrees centigrade. So we are having this as 100 degree centigrade. And it is given that is the surface is at 100 degrees centigrade, and it is given that the T infinity is 25 degrees centigrade. Also the T surrounding is also 25 degrees centigrade, and it is given that the surface emissivity value, this surface emissivity is 0.8, and the free convection is there. So associated convection heat transfer coefficient H is 20 watt per meter square Kelvin. And it is asked to calculate the brick inner surface temperature, that is this T1 value. So it is given T2 is given as 100 degrees centigrade, okay, and T infinity value is given as 25 degrees centigrade. Okay. So now here, if we apply the energy balance, that is what we have studied in the last class, the energy balance. So energy balance states that E in, it states that E in minus E out plus energy generated is equal to change in the energy of the system with respect to time. Now, if you consider this to be a steady state, that means your temperatures are not varying with respect to time. That means your energy is not changing with respect to time. So this time derivative will be cancelled out. Now, if you see this problem, there is no heat generation. That is, there is no conversion of any source of energy into thermal energy. So there is no heat generation within the medium. So the energy generation term will be also cancelled out. So I can have from here that is E in is equal to E out. Now, if you consider the surface here as you are having in the surface energy balance, okay. So in this medium, so if you consider this surface, so since this is a surface, it is not a volume, so it does not store any thermal energy. Okay. So whatever the heat which will be conducted to this surface will be only either convected away or being radiated away from the surface to the surroundings. So I can write the energy entering into this control surface would be the Q conduction, while the energy leaving this control surface would be Q convection as well as Q radiation. So writing the energy in, that is the, in terms of heat flux, I am writing Q conduction is equal to E out, that would be Q convection plus Q radiation. So you can put the values here. So what is the basic law for the heat conduction? It is Fourier's law of heat conduction. So I can write, since it is a heat flux, that is the rate of heat transfer per unit area. So I can write this as K into delta T. So delta T will be here T1 minus T2 upon delta X. So delta X, that is this value. So you can mention it to be as delta X. Delta X. So this will be the heat flux due to the conduction. Now talking about the convection here. So the basic law for the convection is the Newton's law of cooling. That is given as H into surface area into Ts minus T infinity. So surface area and the area normal to the direction of heat transfer are same here. So considering the heat flux for the convection also, so I can write this as H into Ts. So the surface temperature here is T2. So I can write it to be the T2 minus T infinity. So that is the ambient temperature, that is T infinity, plus Q radiation, that is the heat flux due to radiation here. So if you recall, for the radiation heat transfer, I can write effective this epsilon, that is the emissivity of the surface, into sigma into area. Now we are considering heat flux, so we cannot write area here, into Ts to the power 4 minus T surrounding to the power. So this would be the using the basic law for the conduction, convection, and the radiation. I hope up to this term it is clear. So in convection term, what did we use as surface area? It is same area as that we have taken for the conduction. Since this is a plane wall, so this would be the surface area from which this heat will be convected away. So it is same as the area normal to the direction of heat transfer. So either you can take write A here, and same A here. So this will be cancelled out. Yeah. So this is, we are considering heat flux. So we are just neglecting the area. It is a heat transfer per unit area. Okay. Now, if the area was different, if the area surface area was different, area normal to the direction of heat transfer would have been different, and in that case you could have written for the energy input, energy output, then you can have that area terms. But since here AS is equal to the area normal to the direction of heat transfer, you can just cancel it out. I hope now it is clear to all. Okay. So now from this equation, I can determine for the given values of T2, T infinity, H, K, delta X, and epsilon. I can determine the value for the inner wall brick wall temperature. So you can put the values here for the thermal conductivity. It would be 1.2 T1 minus T2, that would be 100 upon delta X, that is 0.15, is equal to H, that is 20, into T2, that is 100, minus T infinity, that is 25, plus epsilon, that is 0.8, sigma, that is Stephen Boltzmann constant value. So you can have 5.67 into 10 to the power minus 8 into Ts to the power 4. So that would be the T2 temperature. This is the surface temperature. So I can write this to be T2 here. So T2 to the power 4, that would be 100. So yeah. So now here, remember, this temperatures are in Kelvin. Always remember that these temperatures are in Kelvin. So we have to write this T2 as here 373. Okay, 373 to the power 4. And this Stephen Boltzmann constant is having the unit as watt per meter square Kelvin. Okay, so T surrounding, that would be 25. So you can have this as 298 Kelvin to the power 4. So from here you can calculate the value for the T1. Now, one of the students is asking that what is the difference between the T infinity and T surrounding. For this question, it is the same. T infinity and T surroundings are the same. While T infinity we consider to be the bulk fluid temperature or the ambient temperature which is flowing over the surface, which is convecting away the heat from the surface. While T surrounding is the surrounding temperature to which the radiation heat transfer takes place from the surface to the surroundings. So there is a difference between the bulk fluid temperature, this T infinity and the surrounding temperature. While in this question, if you see, it is mentioned the question that your T infinity and T surrounding are the same. So now you can equate this and you can get the value for T1. So try to calculate this and tell me the value. 352.5875. So it is in Kelvin, right?
Yes, sir. Yes, sir.
Or is in degree centigrade?
Kelvin, sir.
Kelvin.
No, no, sorry, Celsius. I'm sorry.
Celsius. Okay. So 352.5 degrees centigrade. Everyone is getting this same answer. Okay. So I hope this question is clear to you. How to apply the energy balance and using that how to get the different parameters or different variables which are involved in a heat transfer problem. So we will look into the next question, which is demonstrating the effect of the different modes of heat transfer when there is a medium
Sir, we can't hear you, sir.
So we are having these two parallel plates. So, so for the first case, when there is only atmospheric air between these two parallel plates, what modes of the heat transfer will be involved? Are you all?
Sir, we can't hear you for the past few minutes.
Yeah, tell me.
Sir, we couldn't hear you after the first question.
Oh, okay.
You
Okay. So I will repeat that. So for the second question we are discussing now. So did you able? So you understood now how to solve this the first question?
Yes,
Yes,
sir.
sir.
So
Hello, sir.
Can you show the slide for the second question?
yeah, okay. I will show the slides here.
Sir, I had a small doubt, sir.
Yeah, tell me.
In the first question, in the left-hand side, why didn't we use Kelvin for T2?
Where here?
Yes.
Here you are saying it is a
Yes.
temperature difference. It is a temperature difference. So either you take it in Kelvin or degree centigrade. It doesn't matter.
Okay, sir.
Excuse me, sir.
Tell
In
me.
the first question, in conduction, heat is flowing from left to right, T1 to T2 now.
T1 to T2. Yeah.
So T1 should be greater than T2.
Yeah. Correct.
So T2 we are given 100 degrees centigrade.
Yeah. Correct.
That is 373 Kelvin. And the answer of T1 we are getting is
Oh. Okay. Yes. You are right.
so
So
all the
this
answers are wrong.
is wrong.
All the answers are wrong.
Wrong. Thank you for mentioning it. I didn't notice it. Yeah. So better I will solve it here.
Sir,
It
352
is in
degrees
degree Celsius.
Celsius, sir.
So the answer is in
correct.
Celsius, sir. It's correct only.
Okay,
Yes,
not
sir.
in
Answer
Kelvin.
is in.
It is
Okay.
correct only. This is
Correct only.
Celsius, not in Kelvin. Sorry, very
Celsius.
sorry.
Thank you, sir. Thank you.
Yeah, very sorry. So it is in degree centigrade, not in Kelvin. Sorry. So so it is 100 degrees centigrade. T1 is 352.5 degrees centigrade. Okay. Thank you. So there is any other problem related to first question? Anyone? Any problem related to first question now?
No, sir.
Sir,
Yeah.
sir, can we consider the Q conduction equal to Q convection plus Q radiation for all the questions, which involve heat transfer from surface to surrounding? Because
Yeah.
in the end, the equation will come the same.
Depends upon your problem. Okay. So if it is mentioned that there is some heat being conducted into system and then from the surface it is being convected and radiated away, then you can have energy balance. Even if nothing is mentioned for the radiation, you can considering that radiation is not considered in the question, you can just remove this radiation and you can have Q conduction equal to Q convection. In that case also you will have a problem and you can solve it accordingly using this energy balance.
Okay. Thank you, sir.
Or it might be case where there is no convection heat transfer. Only there is no ambient air or there is no bulk fluid in motion. Only there is a radiation heat transfer from the surface to the surrounding. So in that case, your Q conduction will be equal to Q radiation. So that will be another problem related to this energy balance. You can then also follow the same pattern and you can get your solution for that problem also. I hope now everything is clear related to first question. If anyone has doubt, you can say it now. Okay, then. Let's move to the second question now. So, in second question, are you able to see the slides?
Yes, sir.
So, second question states that there are two parallel plates. So, one is at Kelvin, another one is at 200 Kelvin, and both are separated by a distance of 1 centimeter. Okay, and considering that both surfaces are a black surface, the emissivity value is equal to unity. Okay, and it is given that you have to determine the rate of heat transfer between the plates per its surface area, assuming the gap between the plates is first filled with an atmospheric air. So if you consider that the gap is filled with the atmospheric air, so in that case, what modes of the heat transfer will be involved? First is the atmospheric air. The gap is filled with atmospheric air. So what modes of heat transfer will be here? If there is only air present,
Convection and
Convection.
radiation. Convection and
How
radiation.
big can be convection?
Sir,
I
if the
told
air is
that,
stationary, we need to consider as conduction.
okay,
Conduction, sir.
convection is there, but convection is not possible. Why? Because convection is only possible when there is a bulk fluid motion. Is there a bulk fluid motion here? Is it
No.
mentioned that fluid is moving? No. So when the fluid is not moving, then there won't be any convection process. Since the
Sir,
fluid
what
is
about free
in motion,
convection?
yeah, tell me.
Sir, what about natural convection?
Yeah, natural convection can be there, but its value will be very less. It is almost negligible compared to your conduction and the radiation here. So we can neglect it.
Okay, sir.
Excuse me, sir.
Yeah, tell me.
So if you say ki in this problem where we can't consider convection because there is no bulk fluid motion, right?
Yeah.
So was there any bulk fluid motion in the first problem? Because
Yeah,
uh,
there was a bulk fluid motion in the first problem. It was mentioned that your ambient air is given as 25 degrees centigrade. Yeah, so there was a free convection mentioned in the question.
so
So here we
if they
consider
mention ki there is ambient air, that implies ki there is bulk fluid motion.
when it is given that there is ambient temperature, that means convection process is there. Either it is a forced convection or a free convection. If it is a forced
Okay.
value, then the value for the velocity will be also given to you. If
Okay.
it is
Okay.
free convection, so only the information about the ambient temperature is enough to understand that there is a free convection. Now,
Okay.
in this
Okay.
question, there is not any value of this T infinity is mentioned. That means we can understand that there is atmospheric air. It might be a free convection there, but it has a very low magnitude compared to your conduction as well as the radiation. So here we are neglecting it. So the modes which are involved here would be conduction, that would be from the first plate that is at higher temperature into the medium to that of the lower temperature plate. So the modes involved here would be from Q conduction, and second one would be Q radiation. So we can determine what would be the value for the Q conduction and Q radiation using the basic laws. So you can determine the Q conduction per unit area can be written as K into delta T value. So these two are 1 centimeter apart, okay, and it is flowing through a medium that is atmospheric air. So this would be K air, that is the thermal conductivity of the medium. So you can see in experiment number 7 in your lab, we are having the determination of thermal conductivity of liquids. So it is very similar to that of experiment where we are having two plates, one at higher temperature, one at lower temperature, and there is a liquid placed between them. And we have to determine the thermal conductivity of liquid. So it is a very similar problem. So in this case, I can write that since one of the side is at a higher temperature, one of the side is at lower temperature. So heat conducted through the medium, I can write Q conduction upon area is equal to thermal conductivity of air in temperature difference, that is T1 minus T2 divided by the thickness of the medium, that is delta X. So here the thermal conductivity of air, you can consider it as to be 0.0219 K of air as 0.0219 watt per meter Kelvin. So this would be the thermal conductivity of air. Now you can put it here. So 0.0219 into T1, that is 300, minus T2, that is be 200, divided by delta X. So delta X is 1 centimeter. So you can convert it into meter. So this will be 0.0. So you can calculate the value for Q conduction for area from here. Can you tell me the value?
219, sir.
219. Okay. 219 watt. Now let's come to Q radiation. So Q radiation upon area, I can write it to be epsilon into sigma into T1 to the power 4 minus T2 to the power. So epsilon here is unity. So I can write sigma value, that is Stephen-Boltzmann constant, as 5.67 10 to the power minus 8. Oh, sorry, watt per meter square. Correct. Thank you for mentioning it. This is watt per meter square. So 5.67 10 to the power minus 8 into T1 to the power 4, that would be 300 to the power 4 minus T2, that is 200 to the power 4. While calculating, always remember that this T1 and T2 will be in Kelvin in this radiation law, because Stephen-Boltzmann law is this Stephen-Boltzmann constant is having unit as watt per meter square Kelvin to the power 4. So always take this T1 and T2 in this formula as. So why did you take surrounding temperature as T2? So there is no surrounding temperature. The plate temperature is T2. There are two plates. You can see the slides. I have already uploaded the slides in Google Classroom. You can open it. So the T2 is the plate temperature, the cold plate temperature. Yeah. So from here you can get the value for the Q radiation. So some of you are getting the answer as 368.55. 368.55 watt per meter square. So if I need to mention what was the total amount of the heat transfer from the hot plate to the cold plate through this medium, I can write this to be net Q net upon area as Q conduction upon area plus Q radiation upon area. So here you can sum it, that is 219 plus 368.55. So can you tell me the value for this? Joshi is asking, sir, why are the values so different considering the temperature of the plate is constant? Because one is by conduction and another mechanism is by radiation. So we are just calculating by two different mechanisms what would be the value for the heat transfer here. So the value you all are getting is 587.55. That is 587.55 watt per meter square. So if you are considering a unit area, for a unit area, the net heat transfer would be 588 watt per unit area. Now let us move to the second part of the question, that it is saying that it is evacuated now. That means there is no presence of any air or any medium in there. So there are two plates. This is T1 and T2, and this is 1 centimeter apart. T1 is at 300 Kelvin, T2 is 200 Kelvin. Both are at black surfaces. So now second part is saying that. So Dev Singh is asking, sir, are we here considering that the layer of air is in contact with both plates, has the temperature of the plates? Yes, we are considering that. So if it is present, if the plates are kept and the air is present for a long time, we can consider that one of the layer is having 300 Kelvin, another layer is having 200 Kelvin. The same is the experiment number 7 also. That is the thermoconductivity of liquids. So what I was saying, the second part of the question is mentioning that there is no medium between these two plates. So what mode of radiation will be there? What mode of the radiation? What mode of the heat transfer will be there?
Only radiation.
Only radiation. So in that case, I can write the Q net upon area is equal to Q radiation upon area. In that case, that would be equal to 368.55 watt. This is the second part of the question. Okay. Now, the third part of the question states that, there is one question from Mohit, that what if one plate is not a black body? So if it is not a black body, okay, so in that case, you will have to consider what is the amount of the radiation which is being taking place, considering the emissivity. That type of question we will discuss in the radiation chapter separately. Right now, we are just considering it to be a black surface. We will have a detailed discussion of it in the radiation chapter when one of is a black body, another one is having a different value of the emissivity, what would be the radiation heat transfer. We'll discuss that in detail later on. So, what I was saying that, yeah, for the third part of the question, that is mentioning that there is an insulation between these two medium. So, the insulation is having a particular value of thermal conductivity. So, urethane, if you consider for urethane, so for when there is a urethane insulation there, so K urethane is given as K is equal to 0.026 watt per meter Kelvin. So now what modes of the heat transfer will be involved here? If there is an insulation between these two parallel plates,
So conduction and radiation, sir.
yeah, conduction will be there, radiation. Now, Paresh Shah is saying that all. No, all cannot be possible, Paresh, because there won't be any convection. There won't be any convection. Convection will be only when there is a bulk fluid motion. There is no moving fluid between the medium here. It is an insulation which is being placed. So there is no movement of fluid. So there cannot be an existence of a convection mechanism of heat transfer here. The only possible is conduction and radiation. Okay. So since there is an insulation, mostly it will be by the conduction. So the radiation heat transfer can be considered in the thermal conductivity of the urethane itself. When we are determining the thermal conductivity of the insulation between two medium, so the whatever the radiation heat transfer can be considered in the value of the thermal conductivity itself. So when we are calculating for the heat transfer through insulation, we have to consider the radiation heat transfer also. So we will have a detailed discussion of it in the radiation chapter. So only this conduction will be considered here. Radiation won't be considered. Okay, since the radiation heat transfer
Excuse me,
will
sir.
be a consequence of conductivity. Yeah, tell me.
So there was some issue in connectivity. Your voice was not audible in the middle. Could you please
Again,
repeat the third part?
yeah, we'll repeat it again. So
Okay.
there is an insulation between these two plates. Okay, so either it will be Q conduction or Q radiation. Okay, so the Q radiation is already being accounted in the value of the thermal conductivity of urethane, which is being placed between two plates. So the if we are calculating the amount of the heat transfer through this insulation, we have to consider only the conduction part. So I can write from here the Q net upon area is equal to only Q conduction upon area. Since the thermal conductivity accounts for the radiation heat transfer also. So I'm just writing Q net upon area is equal to Q conduction upon area. So I can have the value for Q conduction upon area, that is value was 219 watt. Sorry, this insulation is different, so you have to calculate it here. So this would be K of urethane into T1 minus T2 upon delta X. So you can put the value that is 0.026 into T1 minus T2, that is 300 minus 200 by 0.01. So you will be getting the value here as 260 watt per meter square. Now there are a few questions given by you here. Sir, can you explain this
Sir,
once more? Yeah. Tell me.
Sir, how is the value of Q radiation already
Yeah.
incorporated into the value of K urethane?
So why is radiation not accounted in the value of K for air? Sir, can you explain this one for? Oh, okay, fine. I will explain this once more. That is, when there is an insulation being placed between these two parallel plates, okay, the modes of the heat transfer here either by the conduction or by the radiation. Okay, since this is a opaque solid material which is being placed between these two plates, so this is blocking the direct radiation heat transfer between the plates here. Okay. Also, the thermal conductivity of the insulating material is already accounting for the heat, for the radiation heat transfer, which may be occurring through some voids or pores in the insulating material. So, the rate of the heat transfer here will be only due to the conduction. We are not considering the radiation here. Since the insulating material, which is being placed here between these two plates, is going to block the radiation. Okay, the radiation heat transfer won't have a very smooth path from one of the plate to the other. It might be through the pores or the voids of the insulation. That would be very less, and it is itself being accounted in this value of the thermal conductivity. Whatever it is, thermal conductivity. So it is being accounted here in the value of the thermal conductivity. What is the whatever the radiation? It might be a minimal, but it is being accounted here in this value. So I can have this Q net by area is equal to only by the Q conduction by area. I hope this is now clear. Now, one question is coming that why is radiation not accounted in the value of K for air? See, here in case of air, okay, there is no blockage of to the radiation heat transfer. It is being occurring from higher temperature plate to lower temperature plate. So, since there is no blockage of the radiation heat transfer here, there is no solid material which is blocking the radiation heat transfer. There is no resistance to it. So, we are considering the Q net is equal to Q conduction plus Q radiation here. Since both are occurring, Q conduction as Q radiation, you can see the Q radiation is having a higher value compared to Q conduction. So both are being involved here. But if you consider insulation being installed here, it is blocking the radiation heat transfer. Well, whatever the radiation heat transfer, it is going to occur only by the means of some through pores or voids into the insulating material. And whatever it is a minimal amount that is being accounted in the thermal conductivity of the insulating material. So we are only writing for the Q net is equal to the Q conduction. Now,
Hello, sir.
yeah.
So small doubt, sir. So this thing applies only to insulators, or does it apply to solids in general?
It applies to solids also. Yeah, solids also. Because if you are placing a solid between two parallel plates, it is going to block the radiation heat transfer. Only the way by which the heat transfer is going to take place is through the conduction. So if you are placing an iron rod, okay, if you are having an iron rod and there are two plates being kept here, okay, this is a copper. So if you are there are two plates now here. So this is higher temperature, somewhat some lower temperature plate is here. So the heat transfer is going to occur through this medium only. That is the copper here. So if I am considering the radiation here, okay, so that is being blocked by the insulating material. Now another question is, so if we had a transparent material, could we consider the radiation heat transfer in the conventional way? Transparent material, that means you are asking that about the transmissivity. Yoshi? No transparent, or it is just with respect to visible spectrum. So we will discuss these things in the radiation chapter. What about the transparent material? Okay. Infrared doesn't penetrate. So we will discuss these things in the radiation chapter. Just now we are discussing the basic concepts here. So here the insulating material is going to block the radiation heat transfer. Okay. And whatever it is will be is accounted in this value for the thermal conductivity, and the net heat transfer will be mainly due to the conduction heat transfer. So we have calculated the net heat transfer for an insulating material. Now the fourth part of this question was that if there is a super insulation which has a apparent thermal conductivity given as K super insulation is given as 0.002 watt per meter Kelvin. So that is a very low value for the thermal conductivity. So if there is a super insulation, that means there is no direct radiation heat transfer because there is an insulation, so it will prevent any direct radiation heat transfer between the between these plates. Also, radiation heat transfer between the sheets of super insulation does not occur. So since it is a very this is a very low thermal conductivity value, so you can say the radiation heat transfer is very minimal. So I can say the Q total here will be only accounted by the conduction heat transfer. So I can write the Q total or the Q net upon area would be K of super insulation into T1 minus T2 upon delta X. So K super insulation is 0.002 into 300 minus 200 upon delta X, that is 0.01. So you can calculate the value here. It is 0.2 watt. So you can see when the value of thermal conductivity is very less, that it is a very good insulation to the heat transfer, then the value of heat transfer is very minimal compared to the other problems which we have seen today. So this is also 0.2 watt per meter square. So you can see for a super insulation, the value of heat transfer is very less. So this is almost 1 by 1000 of that of the heat transfer to the vacuum. So heat transfer to the vacuum, was this value, that is 368.55. So you can see it is very minimal compared to that. So when we have to insulate any material such that there is no heat transfer from it. If you are applying a super insulation, you can decrease the heat transfer from that medium. But the super insulation or insulation of such type is having very high cost. So in the installation of any insulation, we generally consider the cost matter also, or the cost parameter also. So at this point, I have discussed both the questions related to the chapter number 1, that is the basics of heat transfer. Now, if you see your slides here, at the end of your slide for the chapter, yeah, you can see here the figure showing for all the cases. Are you all able to see the PPT, right?
Yes, sir.
Yes, sir.
Yeah. Okay. So there is a discussion at the end of the slide. So it says that there is a microwave oven. So a very good example of heat transfer with all mechanisms is a microwave oven. So here all these three mechanisms or all these three modes of heat transfer are involved. That is the conduction, convection, as well as in radiation. So food is cooked in a microwave oven by absorbing the electromagnetic radiation which is being generated by the microwave tube called the magnetron. So the radiation emitted by the magnetron is not the thermal radiation, since its emission is not due to the temperature of the magnetron. So rather it is due to the conversion of electrical energy into electromagnetic radiation at a specified wavelength. So generally the microwave radiation is being reflected by the metal surfaces, transmitted by the cookware made up of glass or ceramic, whatever it is, and absorbed and converted into internal energy by food, that is especially the water or sugar or fat molecules. So in a microwave oven, the radiation that strikes the food material or chicken, which is shown here in this figure, is generally absorbed by the skin of the chicken here and the outer parts. As a result, the temperature of the chicken at and near the skin rises. The heat is then conducted towards the inner portion. To the inner portion here. Inner parts of the chicken from its outer parts. Of course, some of the heat is being absorbed by the outer surface of the chicken and is being lost to the air in the oven by convection. So in a conventional oven, the air in the oven is first heated to the desired temperature by some electric or gas heating element, and this preheating may take several minutes. So the heat is then transferred from the air to the skin of the chicken by natural convection in older ovens, or by forced convection in the new convection oven that utilizes a fan. So the air motion in convection ovens increases the convection heat transfer coefficient and thus decreases the cooking time, and the heat is then conducted towards the inner parts of the chicken from its outer parts, as in the microwave ovens. So microwave ovens replace the slow convection heat transfer process in conventional ovens by instantaneous radiation heat transfer. And as a result, microwave ovens transfers energy to the food at full capacity the moment they are turned on, and thus they cook faster while consuming the less energy. So a microwave oven is a very good example of heat transfer with all these three mechanisms, that is conduction, convection, and radiation. So at this point, I end this chapter, and I hope all of you have understood the basic mechanisms of heat transfer, the basic laws related to it, and if there is a heat transfer problem, you can apply the energy balance and you can calculate the value of the temperatures or the variables involved. So at this point, I stop this. Yeah, tell me.
So you said that in a microwave oven, the microwaves are absorbed uh, by the
Can you
material,
speak
and
a
then
little bit loudly?
so you said that the microwaves are absorbed and then converted into heat energy, right?
Yeah.
So, but don't the microwaves cause the polar molecules to vibrate? That causes the heating of the food.
Your voice is breaking. What you are saying?
So I'm saying, don't the microwaves emitted cause the polar molecules of the food to vibrate, and that causes the heating of the food?
No, there is no vibration here. Uh, if you are having a microwave oven, you will not see any kind of vibration.
So not
I
so
hope
the
so.
vibration not visible. The molecules are vibrating. So inside only the
So
Yeah,
polar
this is
molecule.
that
I
is
think what Raj is trying to say is the polar molecules, as in the water molecules in the food, they vibrate because of the energy that is irradiated upon them,
yeah.
and this vibration causes a rise in temperature.
Okay. So I will upload one video also related to this. You can watch it. It is from University of Minnesota, I think. So you can watch that video related to microwave oven. You can have a better understanding how it works. So at this point, I stop the class. I think you are having another class also at 10. So at this point, I stop this class. And in next class, we will start with the new chapter, that is the one-dimensional steady state conduction. So thank you.